Good morning. This is our lecture 11, and in the previous lecture we have discussed about the triple S vapor compression cycle, and particularly we have compared the performance of the triple S cycle with the reversed Carnot cycle, and we also tried to see how the property of the property diagram, uh, particularly the shape of the liquid vapor dome, governs actually the COP of the system. Okay, so basically we have two types of losses. One is called as superheating horn and other is called as throttling loss. So basically these two depends upon the shape of the liquid vapor dome. In case we have the positive slope of the saturated vapor line, then we will be having very less superheating horn area, and when we have the high slope of the saturated liquid line, particularly vertical line. So in that case, we will be having actually less throttling loss. Okay. Now we will try to see there are certain things which are done in the cycle, standard cycle, in order to make it more practical, so that if there are certain challenges that should not actually occur. And other important point is, whenever we operate the cycle in practical conditions, it is not always true that cycle will be operating within the fixed limit of evaporator and condenser temperatures. Okay, so there will be chances and there will be conditions when these conditions, particularly the evaporator and condenser temperatures, may increase or decrease depending upon the situation. Okay, so first we will try to discuss about one variant of the triple S cycle, where in the standard cycle some subcooling is actually done. Okay, so first let us study what is subcooling and what is its effect on the cycle. So basically, if I plot the standard cycle on the pH diagram, then my liquid vapor dome looks something like this on pH diagram, and uh, this will be my standard cycle. Anyone is having any doubt in this? So all are knowing about the standard cycle. Now the point is, what is happening at point 3? At point 3, I have some uh, throttling device, and through this throttling device my substance is actually starting at state 3, and at the end I am getting at state 4. So basically this throttling device usually is nothing but a very small orifice. So it's a very small orifice through which actually flow moves. Now what happens, this particular orifice, whenever it is calibrated and designed, it is designed for pure liquid at the inlet. Pure liquid at inlet. So at the inlet of the this particular orifice, there should be actually flow of pure liquid. In case small amount of vapor has come, what will be happening? You know that liquid is having actually very high density. Okay, so if liquid is having very high density and liquid is passing through the small orifice, in that case we will be having good amount of mass flow rate. But in case small amount of vapor is coming, it will be actually decreasing the overall density of the mixture. Okay, because vapor has very low density in comparison to liquid, and ultimately it will be leading to decrease in mass flow rate. So it means that if we have mixture over here, that means if small amount of vapor is coming with the liquid, then we can have significant decrease in mass flow rate across this. Okay, so if across this I have significant decrease in mass flow rate, ultimately what will be happening? After this mass is entering into the evaporator. Okay, so in evaporator also I will be having low mass flow rate. So if I have low mass flow rate in the evaporator, then overall refrigeration effect will be actually decrease. Okay, so overall refrigeration effect will decrease. So that's why we have to, whenever we are operating the practical cycle, because this expansion device particularly the small orifice, is actually specifically designed for handling high flow rates when pure liquid is actually entering into this. So what we need to do is, we need to ensure in the practical cycles that always our starting state to this is actually in the liquid layer. Okay, so for that what we do, we either design condenser in such a way so that instead of point 3 I ends up somewhere at point 3 dash. Okay, and point 3 dash is actually even on the left side of the saturated liquid line. It means state 3 dash is nothing but in the subcooled liquid state. Is this point clear? All are clear with this idea? So state 3 dash is in subcooled liquid state. Now from 3 dash point, if you allow expansion, then in significant portion of the throttling device, your substance will be remaining basically liquid. And then I will be having entry in the evaporator from point 4 dash. All are clear with this idea? So basically what I can do, either I can, whatever my area of the condenser was there, I can increase the area of the condenser slightly more than what is required for reaching the state 3. Okay, so in that case what will be happening, there will be more overcooling in the condenser, and that overcooling will be actually giving me subcooled state instead of the saturated state. And obtaining subcooled state will always be ensuring that the fluid entering into the throttling device is nothing but a pure liquid. Okay, so which will be avoiding this practical limitation of decrease in mass flow rate and the corresponding decrease in refrigeration effect if slight amount of liquid is actually entering into the system. Is this point clear? Now, if you see the effects of the subcooling, you can see over here. Earlier, your refrigeration effect was nothing but H1 minus H4, specific refrigeration effect. Now, your refrigeration effect with subcooling has become equal to H1 minus H4 dash. And we can see over here that H4 dash is nothing but less in comparison to H4. Okay, because H4 dash will be equal to H3 dash. H3 dash is in the subcooled state and H3 is saturated state. So subcooled enthalpy will be less in comparison to saturated enthalpy at the same pressure. Okay, so that's why what I will be getting that the subcooling leads to what? What subcooling has done? It has increased the specific refrigeration effect. Okay, so on refrigeration effect actually it is having positive impact. Is this one clear? And if you see the work of compression, so that will be actually H2 minus H1. So work of compression over here remains almost unaffected. Okay, so that is the reason it will be even good for improving the COP of the cycle. Then second important point is actually superheating. So basically when we are talking about the superheating, of course from the standard cycle itself you can see that the only possibility of superheat lies with point 1. Okay, so point 1 is where the exit state of the evaporator. Now again, why we need to do slight superheating over here? What are the challenges associated if say instead of 1 I enters over here? What will happen in the practical conditions? If some liquid goes into the compressor, what will happen? It can work. If small droplets are going, what will happen? Yes, so first point is if liquid droplets flows with the vapor, so what will happen? The velocity of the liquid droplets will be having more momentum and it will be actually damaging valves etc. Of the compressor. So high velocity of liquid droplets will damage compressor components. Okay, Other thing, normally, what are the compressors? Either we use the reciprocating compressors or we use the rotary compressors. Okay, and mostly positive displacement compressors are used for these applications. Even in certain cases, centrifugal compressors are also employed. Okay, so whenever we are using the reciprocating piston cylinder based arrangement for compression process, what will be happening? There will be significant amount of friction in between the piston and the inner walls of the cylinder. So what ultimately is done in the practical scenarios, lubricant is actually added so that we can avoid the friction. Now what happens, whenever a liquid refrigerant enters into the piston cylinder arrangement, then liquid has more tendency to stick to the lubricating oil and then carry the lubricating oil along with it. Okay, so if liquid will be carrying the lubricating oil, ultimately what will be having? We will be finding there will be deficiency of the lubricating oil in the system, and ultimately that will lead to increase in friction and increase in the compressor work. Okay, so liquid has more tendency to carry lubricating oil. You can simply understand that if I say you have vapor medium present in this room, okay, and there are some dust particles also. So your dust particles will not stick to vapor. But if I say there is liquid fine droplet present and there is dust particle, so dust particle will immediately try to stick to the liquid. Okay, so in the similar way, liquid tries to carry the lubricating oil, and that will be actually decreasing the lubrication and increase the friction in the piston cylinder arrangement. Okay, and of course we also know that if what happens, some liquid droplets enters with the vapor, then during the compression stage what will happen, we will be finding some point where pressure will within the compressor will suddenly increase. Okay, under that increased pressure condition, if the temperature of the liquid droplet is becoming sufficient enough for vaporization process, then suddenly that liquid droplet will be changing into vapor. So if a liquid quantity changes into vapor medium, there will be significant increase in volume. Okay, because liquid to vapor conversion, the density of the substance is changing from very high value to very low value. So there will be significant increase in volume. That significant increase in volume can lead to significant pressure oscillations within the system, ultimately which will also be detrimental for the performance of the compressor. Okay, so conversion of liquid droplets to vapor, that is again problematic. So these are some of the challenges. Even if small amount of liquid enters into the compressor, these type of adverse effects can happen. Okay, so always our effort will be to actually reach to a state at the inlet of the compressor, which is actually what? Which is superheated. Okay, so that's why instead of on my pH diagram, if I go, instead of starting from point 1, my attempt will be to go to some point 1 dash. Okay, and 1 dash point is nothing but the superheated state. Is this point clear? So 1 dash point is superheated state. Now, how we can do this superheating? One way is we can have slightly bigger evaporator, so it will be there within the evaporator only. The other way is because sometimes in the evaporator also we cannot purely decide, because within the evaporator what happens, there is liquid vapor mass exchange, liquid vapor heat transfer. Okay, conversion of liquid to vapor, and mixture is actually getting the heat from the surrounding. So it always becomes challenging in a two-phase mixture to exactly predict the exit state by exactly controlling the size of the heat exchanger, and also in the variable loading condition it will be actually challenging to control. But still, we have one opportunity. Whenever the refrigerant will be coming at the exit of evaporator, from the exit of the evaporator to inlet of the compressor, there will be some pipeline. Okay, and usually the evaporator temperature is in the range of, if we are going for air conditioning application, then it will be in the range of 0 to 5 degrees Celsius working fluid within the evaporator or at the exit of the evaporator. And if we are even going for, say, this one domestic refrigerator applications, particularly in the ice chamber, etc., their temperature can go up to minus 15 to minus 20 degree Celsius. So it means that at the exit of the evaporator, always there will be what? Always there will be very less temperature in comparison to the ambient temperature. Okay. So one thing is that if we simply expose the pipe from the exit of the evaporator to inlet of the compressor to ambient, then there will be some heat leakage from the ambient to the evaporator tube, and ultimately it will be leading to heating of the refrigerant in the that particular tube. So ultimately you can achieve superheating without doing any extra effort. But
internally reversible.
of course, internally reversible it can be if it is under the constant pressure. Externally it will not. Okay, is this one clear? Now, what is the challenge over here? Shall we go for this? We need not to do anything. In the pipe, whatever insulation we provide, we just need to remove that insulation. But is it a good idea to do? Is it a good idea? Shall we do it or not? Please tell me. Why not? Why should we not do it? You will be understanding that superheating can go up to any high temperature. We don't have any issue. So there is one issue actually. So if you see, the constant entropy lines on pH diagram basically diverges when we move significantly away from the this one, significantly away from the saturated vapor line. So ultimately what will be happening, if this was my process 1 to 2, in the superheated regime, my process 1 to 2 dash will be something like this. Okay. Now if you check the length of 1 to 2, projected length on horizontal, this is your H2 minus H1, and projected length of 1 dash to 2 dash is how much? This is H2 dash minus H1 dash. So first point is superheating significantly increases the compressor work. You can see the projected length is significantly large in comparison to the projected length in the previous case. Is this one clear? So it means superheating has led to significant increase in the work. Now the second important point is, if I only do the superheating from the ambient heat leaks, then what will be happening? From point 1 to 1 dash, whatever I am having, that is actually not the actual refrigeration effect, because refrigeration effect will only be coming from the refrigerated space. Okay, so refrigerated effect is remaining again same, H1 minus H4, but work of compression has increased. So it means that COP of the cycle will be decreasing significantly. You are keeping the same refrigeration effect, but you are increasing significantly the work input to the device. So ultimately the COP will decrease significantly, and if you make certain mechanism that this superheating can happen within the system itself, then this superheating can also be added into the effective refrigeration effect, and it can actually control the decrease of COP, or it can actually uh, avoid the significant decrease of the COP. Is this one clear? So that's why by just exposing the tube of the exit of evaporator to inlet of compressor, though it will be solving this purpose of always ensuring the safety of the compressor, however, what will be the challenge? The challenge will be that it will lead to significant amount of work input for the almost same refrigeration effect. Is this one clear? So, what is the solution? Other solution could be that over here our aim is to do subcooling, and here our aim is to do superheating. And if I now compare the temperatures, temperature at this point, particularly saturated point, is significantly high in comparison to temperature of saturated vapor at the exit of the evaporator. Now if I use a common heat exchanger through which I pass first the refrigerant from the exit of the evaporator, then these will be exchanging heat among themselves, and I will be having actually subcooling driven only because of the refrigerant itself. I need not to put any extra effort for subcooling at the exit of the condenser. Is this one clear? So my two issues will be resolved simultaneously. Are you agreeing to this point? So what I'll do now, I'll use a system where this is my condenser, this is my evaporator, and say this is the expansion device. So refrigerant has come from expansion device, it has entered evaporator. From the evaporator, refrigerant has come at state 1, and after that, before passing through the compressor, I have passed it through a heat exchanger. So this is the additional heat exchanger, and in this heat exchanger, from one side this fluid is going, and then it is entering into the compressor and then into condenser, and other side whatever is coming out of the condenser at state 3, that substance is actually passed through this heat exchanger and then it is entering into the expansion. Is this one clear? So in this way what will happen? From 3 to 3 dash, whatever cooling, because temperature of 3 which is entering to this heat exchanger from the top is greater in comparison to temperature of state 1 which is entering from the other side. So there will be heat transfer from this to this. Because of this, it will be heating from point 1 to point 1 dash, and it will be cooling from point 3 to point 3 dash. Okay, so now earlier what I was telling you that one can do subcooling by increasing the size of the condenser. You need not to increase the size of the condenser. You can keep condenser size as required for achieving the saturated liquid state, and after that you can use one additional heat exchanger, very small heat exchanger, in which we can actually do this type of arrangement, and this type of arrangement will be actually facilitating both the subcooling as well as the superheating. Okay, and what is the advantage of this? Now you can see that if I plot the pH diagram, how it will be looking like? This is point 1, and point 1 to 1 dash is now taking place where? In the heat exchanger. Then from 1 dash to 2 dash is work, then 2 dash to 3 is taking place in the condenser, and from 3 to 3 dash is in heat exchanger, and then of course we have the expansion device. Okay, now refrigeration effect is again H1 minus H4. But whatever this addition of 3 to 3 dash is happening in the refrigeration effect, that addition is purely coming because of the heat gain by the fluid in the superheater. Okay, and ultimately for this intermediate heat exchanger, because whatever mass flow rate is coming from here, same mass flow rate has passed through this. So mass flow rate of this side and this side both will be same. Is this point clear? Mass flow rate of this stream and this stream will be same. So ultimately, if I do energy balance, I can write mass flow rate into H3 minus H3 dash, that is the heat lost by hot part, has to be equal to m dot into H1 dash minus H1, which is the heat gained by the cool part. Okay. Another interesting point is m dot will be cancelling out. This H3 minus H3 dash I can write Cp into, it is the pure liquid. So in the pure liquid I can write Cp into T3 minus T3 dash, and this Cp is of F. F means I am referring to liquid state, and here this H1 dash minus H1 can be written as Cp of what? Vapor. Okay, because here at point 1 is nothing but in the vapor state. Cp of vapor into T1 dash minus T1. Now you understand one point very clearly. Which Cp is larger? Fluid Cp is larger. Okay, yes. Okay, so we have thermodynamically relation dH equal to TdS is equal to dH minus Vd. Is this one clear? So this is one of the thermodynamic relation we have, and whenever say I have over here pure liquid and I am heating this pure liquid under the constant pressure condition. What is the meaning of constant pressure? Whenever I will be heating, if there is any increase in pressure, then piston will keep on expanding till the we are able to achieve the constant pressure. So for constant pressure condition, this dP will become equal to 0, and TdS is nothing but for the internally reversible process, delta Q is equal to TdS. From here, delta Q will become equal to dH. Is this one clear? Now, what is the fundamental definition of the Cp? The fundamental definition of the Cp is amount of heat required to raise the temperature of a substance by 1 degree. So it means under constant pressure condition. So it means it will be nothing but delta Q by delta Q by dt, amount of heat added per unit temperature at constant pressure condition. Okay. Now under this condition, what you will be finding? You will be finding that delta Q is equal to dH by dt for constant pressure. And from here, you will be finding that dH is equal to Cp into dt, but this will be applicable only when my pressure is, process is actually constant. Okay. So Cpf is equal to T3 minus T3 dash, and remember this point. So this I can apply only when pressure is constant. Okay, so that you have to remember basically. And even in case of your gases, you can even restrict this condition, because for gases, this one enthalpy is only a function of temperature. Now what I am saying is Cpf is equal to T3 minus T3 dash. and this CPV is T1 dash minus T1. CPF is nothing but specific heat of liquid, which is significantly large in comparison to specific heat of the vapor. So what I will be getting the temperature conditions? T3 minus T3 dash will be small in comparison to T1 dash minus T1. So it means this heat exchanger will be majorly ensuring that my state at the inlet of compressor is always super. Is this point clear? So I will not be having any issue over here. And the other point is, whatever this 3 to 3 days thing, which for achieving this thing earlier, if we were increasing the size of the condenser, then we would have to put the additional cost. Okay, and whenever it is exchanging the heat with a substance which is at significantly lower temperature, then the heat exchanger area required will be very less in comparison to the area required if I simply cool it from the ambient air or ambient water. All are agreeing to this point? Because whenever you have large temperature gradient, then rate of heat transfer is high and area required is less. Is this one here? So whenever I use this new heat exchanger, then the inlet area is T3 and this area is T1. Sorry, this temperature is T1, which is significantly less in comparison to the ambient temperature. So their temperature difference is large. So it means among these two, the rate of heat transfer will be high. So if rate of heat transfer is high, then this heat exchanger area required will be very, very small. But instead of this, if I cool this point from 3 to 3 dash by using only the ambient air, then rate of heat transfer will be low and area required of the heat exchanger will be high and overall weight of the system will be increasing. So this is the advantage of combining subcooling and superheating together, so that with less weight of the system we can achieve the good practical system. Is this point clear? Why subcooling and superheating is required in practical cycles? Now let's try to see, because in the cycle we have actually multiple conditions. Multiple condition means we have evaporator temperature, we have condenser temperature, evaporator pressure, condenser pressure, then we have different types of working fluid. There will be some refrigerants whose latent heat of vaporization will be different, whose ratio of Cp by Cv will be different. Okay, so we have large combinations and significant amount of variations in the system. Moreover, you have to also know one important point, that whenever AC or fridge is in the off conditions, then its evaporator and condenser temperature both are corresponding to the ambient temperature conditions. Okay, so when I switch on the system, then initially it is in the transient phase where evaporator temperature is decreasing and condenser temperature is increasing. Okay, so in that transient phase, how my requirement of the work changes, so that I can actually correctly design the capacity of the compressor motor. Otherwise there can be failure, etc. Okay, so all these things actually we have to now understand. So let us first try to study the effect of evaporator temperature. Say this was my cycle. Please try to see that the line 3 to 4 should be dashed. Sometimes I am drawing it as a solid line. Okay. So now let's consider that if I have to decrease the evaporator temperature, then what will happen? If I decrease evaporator temperature, then I have to go to this point, somewhere below T1. Is this point clear? Now, if I am going here, along with decrease in the evaporator temperature, evaporator pressure will also be decreasing. Okay, so whatever effect I am trying to explain it for the temperature of the evaporator, same will be applicable even for pressure of the evaporator. Is this point clear? So what will happen if I decrease the evaporator temperature, then I will be ending at some point 1 dash, and moreover expansion also I have to do up to point 4 dash. Is this one clear? And then from 1 dash I will be having basically the compression process, and I will be getting to some point 2 dash. So one important thing you can observe over here, earlier your refrigeration effect was H1 minus H4, sorry. But when you decreased the evaporator temperature, then what has happened? Refrigeration effect has become H1 minus H4 dash. Now if you see, H4 is equal to H4 dash, because you are starting from the same inlet point, and in an isenthalpic process enthalpy will remain same. Is this one clear? So H4 is equal to H4 dash. But what is changing? H1 dash now is less in comparison to H1. Of course it is not much less, but slightly less in comparison to H1. Whether it is more or less, it will always be depending upon the slope of saturated vapor line. And of course the nature of slope of saturated vapor line will be different for different refrigerants. But over here majorly we will be having in this region the positive slope of the saturated vapor line. So if we have positive slope of saturated vapor line, if H1 dash is less than H1 and H4 is equal to H4 dash, then what will happen to the refrigeration effect? Decrease. So refrigeration effect decreases when I decrease my evaporator temperature. That is one thing we have got. And other important point is, what happened to the work done? Work done has increased. Okay, so compressor work has increased because H2 dash minus H1 dash is larger in comparison to H2 minus H1. So it means work done has increased. Here only our job is not complete. So from here easily we can conclude that by decreasing the evaporator temperature, your COP will be decreasing. So one important point is, during summers our COP of the AC and fridge is less. During winter COP of the AC and fridge is more. Okay, so that we can conclude, but more that we can conclude from the condenser temperature, that I will discuss further. But here only our task is not solved. One interesting point has happened, that when I moved from point 1 to point 1 dash, what happened to the temperature of the refrigerant? Temperature of refrigerant has decreased. So when temperature of the refrigerant decreases, what happens to specific volume? Increase or decrease? With decreasing temperature, density increases and specific volume decreases. Okay, so specific volume is decreasing. So what will happen to the volumetric refrigeration effect? Please tell me. I have defined one term which was volumetric refrigeration effect. H1 dash minus H4 dash divided by nu 1. So earlier your volumetric refrigeration effect was H1 minus H4 by nu 1. Now it is H1 minus H4 dash by nu 1 dash. Okay. So your nu 1 was large and nu 1 dash is smaller. So if this is smaller, it will try to increase the volumetric refrigeration effect. But overall it will be depending upon the combined effect of enthalpy and the specific volume, which one is actually dominating. Is this point clear? volumetric refrigeration effect we take into consideration, because ultimately what will be happening, you have some reciprocating compressor which is allowing the refrigerant to flow through it, and usually the displacement volume of the reciprocating compressor is always fixed. Let me explain this. Say this is your reciprocating compressor. So what typically has a reciprocating compressor? A suction line and a discharge valve, and then you have a piston. Whenever this piston is moving in downward direction, then your suction port is open and fluid is actually entering inside this. And whenever it is moving in the upward direction, then discharge port is open and fluid is going out of this. Now, if say above is the clearance volume and this is the top dead center and this is the bottom dead center. So piston will be displacing in between top dead center and bottom dead center. In this one, say it is completing L amount of length, which is called as stroke of the piston. And if inner diameter of this cylinder is D, then how much will be the displaced volume? The displaced volume will be equal to pi by 4 d square into L. This is the displaced volume. Now, usually what happens, theoretically what should happen, whatever is the displacement of the system, that should be the actually fluid which is coming inside and that is going outside. Okay, but usually what happens, we have to provide some clearance at the top so that piston should not hit on the head of the cylinder. In this clearance volume, some amount of fluid is actually left always. Okay, whenever you do the suction effect, the pressure within the system decreases. So when pressure within the system decreases, whatever the left fluid was there at the exit of the discharge stroke, its pressure was high. Whenever pressure will be decreasing, it will try to occupy more amount of volume. Okay, so it means it puts some penalty on the volume. So as it is putting some penalty on the volume, the actual volume which is coming inside and going outside must be multiplied with one quantity which is called as volumetric efficiency. So that's why we define one more volume which is called as swept volume. Swept volume is actual amount of volume sucked in and supplied out. So swept volume is equal to volumetric efficiency of the compressor multiplied by pi by 4 d square into L. Is this point clear? Agreeing to this point or not? Because the clearance volume puts some penalty. Because of that penalty, whatever the displacement has taken place, that is not entirely converted into the useful volume. So for that penalty, we write over here volumetric efficiency. Now what happens? This piston continuously keep on moving. As it continuously keep on moving, of course it will be having some, say N is the RPM. So if N is RPM, then what will be the swept volume flow rate? V dot S. Swept volume flow rate will be volumetric efficiency into pi by 4 d square L into N is number of revolutions, and if you have to calculate per second, so this was RPM per second will be by 60. Is this point clear? Now one thing can come is, in place of a single cylinder you can have multiple cylinders in the compressor. So it will be then depending upon number of cylinders, NC also. So NC over here is number of cylinders. So this is the volumetric flow rate. Now what will be mass flow rate? Mass flow rate of the refrigerant which is passing through the compressor, that will be equal to V dot S, volumetric flow rate, divided by specific. Is this point clear? So now from here mass flow rate comes out to be volumetric efficiency of the compressor into pi by 4 d square L N by 60 into NC divided by V. So it means that if your specific volume increases, what happens? If specific volume increases, the mass flow rate across the compressor will be decreasing, and if specific volume decreases, mass flow rate will be increasing. So that is the reason volumetric refrigeration effect is important. Is this one clear? Okay, so effect of evaporator temperature is clear. Now let's talk about effect of. Shall I need to repeat it again, or this compressor effect is clear to all? Is it okay? Next, let's talk about effect of condenser temperature. Of course, along with the temperature, pressure is also coming into picture. Okay, because it's a saturated state, and in saturated state, pressure and temperatures are dependent. Okay. What will happen over here? Please tell me. What will be happening over here? You can do it by your own now. Draw pH diagram. See, the point is, whatever you will be studying in RAC, you should know the fundamental ideas. Rest is just application. If you are knowing exactly what are the fundamental principles, then you can easily apply these for solving all the refrigeration problems. It's just the applied part. Okay. So your fundamental idea should be clear. Now you see, this is your if I increase condenser pressure or condenser temperature, what will happen? Instead of this point, I will go up to some point 2 dash. Now from 2 dash to 3 dash, and then 3 dash to 4 dash. What has happened? Refrigeration effect has, from here you can clearly see that H1 minus H4 dash is significantly smaller than H1 minus H4. It means refrigeration effect has decreased, but again I have drawn it exaggerated. Generally this line is very vertical. Okay, so generally this line is vertical. Because of this, upon increasing the condenser temperature or pressure, change in refrigeration effect is very, very small. Of course it decreases, but decrease is very, very small. Is this point clear? All are agreeing to this point or not? Fine. And because usually this line I have too much made it inclined, this line is more of a vertical. So more, because it being vertical, the change in point 3 and 3 dash will be very, very small. Is this point clear? So with condenser, increasing the condenser temperature, the changes in refrigeration effect is there, it decreases, but the decrease is very, very small. On the other hand, if I talk about work done, compressor work increases significantly. Okay, compressor work increases significantly. That is very clear to you from the two points. One is the constant entropy lines keeps on diverging, so their slope keep on decreasing. If slope is keeping on decreasing, the line will try to become more horizontal. More horizontal means it will take more work. Okay, and other is pressure ratio across the compressor has increased. So now compressor is changing the pressure from to a larger value. So if it is changing to larger value, of course it will increase. Okay, work will increase. So work increases significantly. So because of this, the COP will be actually decreasing significantly. That is the reason in summers your temperature, ambient temperature is close to 35-40 degrees Celsius. So refrigerant in the condenser has to be above than that. Say refrigerant has to be at a temperature of 55 or 60 degrees Celsius. Whereas in winters, ambient temperature is 20 degrees Celsius. So refrigerant can go only up to 25 or 30 degrees Celsius after the compressor. Okay. So it means that in winters, and of course your inlet state, if you are operating a freezer, inlet state, if you have to make ice, that will always be remaining same in both the seasons. Okay. So in winters then you have good amount of saving because your condenser will be operating at the low temperature. So in winter actually the COP of the fridge is actually very high, whereas in summers the COP decreases. If I try to plot now combined effect of temperature and pressure on COP, you will be finding that with evaporator temperature, increase in evaporator temperature, what happens? COP increase or decrease? Decrease. If you increase, COP will increase. Correct. So you will be getting effect something like this. Now what are these multiple lines? Here is multiple lines are multiple condenser temperatures. What will happen with increasing condenser temperature? COP will decrease. So this is the direction of increasing condenser temperature. So COP generalized effect, you can plot it like this. As you increase the evaporator temperature, your COP increases, and whenever you decrease the condenser, when you increase the condenser temperature, then COP decreases. One important point you can observe over here, whenever I have plotted this line and this line, where slope is increasing more steeper, for the low condenser temperature. At low condenser temperature, the changes in evaporator temperature lead to significant increase in COP upon increasing the evaporator temperature. Whereas for very high condenser temperatures, the increase of evaporator temperature will be having, of course, it will be having some effect on increasing the COP, but the amount of effect will be less in comparison to the effect which is observed at the high, at the low condenser temperatures. Is this one clear? All are agreeing to this point? Okay, maybe we will talk about pull down and compressor work in the next lecture.